Hello everyone, and welcome to the next video in the series. This is the second Masterclass video, and in Masterclass videos my aim is to go deeper into topics that we have already talked about. And in this particular video we will have a chance to have a glimpse into the power of algebra. Now, a number of issues that I would like to talk about in this video, and to make things smooth, I will start with where we left off with money problems, where we talked about discount and tax. Now, one of the things about algebra is that although context changes from one problem to another problem, we'll find that the kinds of tools that we use to solve certain problems are similar. An example of that is problems in which we deal with tip. These problems are very similar to tax problems. Take a look at this problem. It says the haircut costs $32.99. How much tip should I add if I wish to leave a 15% tip? Now, this is similar to a tax problem. In fact, it could be that an item is priced at $32.99. How much tax? Calculate the amount of tax if tax is added at 15% of the price. So if you're looking for the amount of tip, it's very similar in terms of the logic that goes into solving it. It's very similar to amount of tax problem. And if you're looking for the grand total that you have to pay, including tip, that would be similar to the grand total that you have to pay if tax was added. For this problem, the key sentence is that the amount of tip is 15% of the cost. And that this is again similar to saying that the amount of tax is 15% of the price. With this in mind, we can write an algebraic solution with A representing the amount of tip in dollars. A becomes equal to, or the amount of tip becomes equal to 15%. So I convert from percentage to decimals, 15% of the cost. So again, you see, that's how you read it. Amount of tip is 15% of the cost. And then we multiply 0.15 and $32.99 to find out that the amount of tip is $4.95. Problem number 2, same haircut costs $32.99. How much should you leave in total this time if you wish to add a 15% tip? So problem number 1 was similar to an amount of tax problem. We only computed the amount of tip. Problem number 2 is similar to a grand total problem. And the key sentence here is that the grand total is 115% of the price. And in this case, perhaps we should say the cost. And so it's very similar to a grand total problem when you find 100, let's say 13% of the price, assuming tax is added at 13%. Or this one, we could actually reword this and turn it into a grand total problem where tax is added. We could say that the item is priced at $32.99. Calculate the grand total if tax is added at 15%. With the grand total being 15% of the cost, we can now turn that into an equation with T representing total amount of money that I should leave in dollars. The total comes to 115%, so that there's your 100% plus 15%. So 115% of the cost, which is $32.99. So the total is 115% of the cost, which is $37.94. And therefore in total I should leave $37.94. So here was a tip problem, which was in terms of the kinds of tools that we use to solve it, it's very, very similar to amount of tax problems. And there are other kinds of problems. Some of them involve money, some of them don't. As you saw in the video on general percent problems, there were many problems which exhibited a growth, and we wanted to find the amount of growth, or we wanted to find the grand total after. And for all of those, we used similar tools and techniques. Here's a third problem. Now this one is in investment, and it says that you want to invest $40,000 in an account that pays simple interest at a rate of 1.25% per year. How much will you earn in interest after 1 year? Now, here we have, now I should mention that there are many different kinds of investment schemes, and this is probably one of the simplest ones, amongst the different ones that we have. This is one of the simplest. And for that reason, I suppose that's why they call it the simple interest rate kind of a investment. But basically, what this kind of investment says is that the amount of interest that I will get at the end of the year is 1.25% of the amount that I invest. And with that in mind, the algebraic solution A being the amount of interest earned after 1 year in dollars, A becomes equal to 1.25% of the money that I invested, $40,000. And this comes to $500. So after 1 year, I will earn $500 in interest. Problem number 4, same kind of investment. You want to invest $40,000 in an account that pays simple interest at a rate of 1.25% per year. What will your account balance be after 1 year? So here we're looking for the grand total, the initial investment and the interest on top of it. And the key sentence is account balance after 1 year is 101.25% of the investment. For an algebraic solution, with A representing the account balance after 1 year in dollars, A becomes equal to 101.25% of the investment. So again, A is 101.25% of the amount that I invested, which is $40,000. And this works out to be $40,500. So after 1 year, my account balance will be $40,500. Okay, so this is one of the things that algebra does for us. It shows similarities in tools that we use to solve problems. In addition, sub-expressions always point to certain class of problems. We have talked about sub-expressions earlier when we talked about conversion of units. And I would like to take up the topic again. And here's a problem that we have, number 5, that says a book priced at $37.99 is on sale at 15% off. Tax is added to the sale price at 13%. So this is a discount followed by tax problem. And now 2 questions. One, part A, what percentage of the original price is the grand total? And part B, is the combined effect of the discount and tax an effective discount or tax? So when you have discount followed by tax, with discount you pay less, and then when tax gets added you pay more. And the question is, in the end, when we take into account the effect of both the discount and the tax, will you end up paying a little less than the price, which would be similar to an effective discount kind of a problem? Or will you end up paying a little bit more than the price, which would be sort of like more similar to a tax problem? So let's see how we can go about solving these problems. And one of the interesting things that you should pay attention to is that I'm going to use semantics to solve part A. So we begin with the equation that we normally would set up for the grand total. We start with the price, $37.99. And because it's on sale at 15% off, we will pay 85% of the price. So that's what this does. 100% minus 15%. That becomes 85% of the price. So these 2 factors together compute the sale price. And then to find the grand total, we find 113% of the sale price. Okay, so that was the approach that we used to set up an equation for this problem. Now, the key to solving part A is to take a look at what I have highlighted here, the 2 brackets, 1 plus 0.13 times 1 minus 0.15. The answer to part A is in the result of calculating what I have highlighted here. And let's see how that works. How is it that if we take 1.13 and multiply it by 0.85, we will end up answering part A? Now, to explain how that comes about, let's take a look at the question one more time. In part A, what percentage of the original price is the grand total? So I have repeated that here. Now, if you think about how you would use words to answer this question, you would probably make a sentence similar to this. The grand total is some percentage of the original price. That's exactly what they ask for. And if we can find this value here, we have answered the question. Again, what percentage of the original price is the grand total? So the answer would be the grand total is some percentage of the original price. We have to find out what that value is. To work it out, so in mathematical notation, then that sentence I can write it down as T, the grand total, is some percentage of the price. If we can figure out this number, we have answered the question. Okay, now let's take a look at the equation that we would normally set up to find the grand total, the one that I displayed just a minute earlier. So here we have T equals 113% of the sale price, which is 85% of the price. And now here's the highlighted part. And if you compare what we would like to do here, which is find out what number goes with the percentage, and the setup that we have here, you notice that the answer to the question that we have here is pretty much given by the multiplication of these two brackets. And if we work this out, we get T equals 113% times 85%, or 1.13 times 0.85. And working it out to a single number, the grand total becomes 96.05% of the price. And that's exactly what we wanted to find. Grand total is some percentage of the price. So the factors that we have that go with the percentages, such as 113% and 85%, when you multiply them, you pretty much find an effective kind of percentage that relates the grand total to the initial price. So for an algebraic solution, with R being the percentage of the price, that is the grand total, unit 1 of course, R becomes equal to, now that's the part that will answer the question. So the rate that we are looking for, the percentage, is equal to 113% times 85%. And if we multiply them, we end up with 0.9605, which means that the grand total is 96.05% of the original price. Now for part B, is this an effective discount or an effective tax? This would be similar to a discount problem because we are paying less than 100% of the original price. So in the end, the effect of the 13% tax and the 15% discount is to give us something close to 4% discount. Whether it ends up being a tax or discount depends on what you get after you work out your percentages, after you multiply, let's say in this particular problem, 113% and 85%. If this value is less than 1, then that means that you pay less than 100%, and therefore it's like a discount problem. If the value is 1, then you pay the price. It's like there is no discount and there is no tax. And if R turns out to be more than 1, that would be more than 100%, then you will be paying a little more than the original price, and this makes it similar to an effective tax problem. Okay, so one of the things that we just noticed is that if we take some of the factors in the equation that we had and we multiply them, we end up answering the kinds of questions that we saw in the previous problem. This kind of situation is common to problems in different contexts. Let's take a look at some of these problems. Problem number 6 says the context in this problem is money. And the problem says, same as the problem that we just looked at. The problem says a book priced at $37.99 is on sale at 15% off. Tax is added to the sale price at 13%. Calculate the grand total. And for this problem, the equation that we had was that the grand total is, we begin with the price, $37.99, and then find the sale price, which is 85% of the price, and then find 113% of the sale price. And we just noticed that if we work out the highlighted part, we'll end up with a percentage that's close to 96%. So the grand total is roughly about 96% of the price. In this problem, what's happening in multiplying, in working out the highlighted part, is, let's take a look at the diagram on the right side. The top equation tells us that in order to go from price to sale price, we have to multiply by 85%. That's what this part does. So in effect, multiplying by 85%, multiplying the price by 85%, will give us the sale price. And then once we have the sale price, we can multiply by 113% to find the grand total. And when we perform the calculations that are in the highlighted part, and we end up with 0.9605, what we do then is we are saying that if we want to go from price to the grand total without having to bother with the sale price, we can multiply the price by 0.9605. You can see that in the equation. Here's the price. Multiply by 0.9605, you get the total. And same thing here. So multiplication of these two factors, in effect, what it does is that it removes an intermediate link and connects the beginning to the end. Now let's take a look at another problem. Conversion of units. The problem says the beam has a length of 152 centimeters. Convert this to feet, given that 1 inch is 2.54 centimeters and 1 foot is 12 inches. And if you recall, this is the equation that we set up to solve this problem. Starting with the length whose unit we want to change, 152 centimeters, we use the relationship 1 inch is 2.54 centimeters to convert the unit to inches. And then we use the relationship 1 foot is 12 inches to convert the unit to feet. And the connection between these two factors, the way they behave, is so similar to the way these two behaved. And if you notice, these two factors here allowed us to go from the start to an intermediate value and then from there to the end. And when we multiplied them and reduced that to one number, we pretty much connected the start to the end. The same thing happens here. If we were going to work this problem out, let's do the divisions. 1 divided by 12 is 0.0833. The unit is feet per inches. And then 1 inch divided by 2.54 is 0.3937. Unit is inches per centimeter. And then we multiply by 152 centimeters. And of course, we can finish the highlighted part, multiply 0.0833 and 0.3937 to get 0.0328. And if you take a look at what's happening here, and let's go back to the diagram again. Now here we have length in centimeters, that's what we start with. And then if you multiply by 0.3937, which is the same as multiplying by 1 over 2.54, you effectively change the unit from centimeters to inches. So multiplication by 0.3937 converts the unit of length from centimeters to inches. And then once we have the length in inches, we multiply by 0.0833 to convert the unit from inches to feet. And that's what the second multiplication achieves. So again, factor number 1 going from factor number 2, I suppose this is factor number 1. Factor number 2 going from right back is 0.3937, and multiplying by that factor converts the unit from centimeters to inches. And then going to the next factor, multiplying by this one, will convert the unit from inches to feet. And when we multiply these, of course, inches cancel out, and we end up with feet per centimeter, and we get 0.0328 feet per centimeter. And what this does is that it bypasses the need to convert to inches. It goes now straight from centimeters to feet. You can see that from the equation as well. You start with centimeters, multiply by 0.0328 feet per centimeter, and you find the length in feet. Here is an everyday life problem. This car uses fuel at a rate of 6.5 liters for every 100 kilometers. Fuel costs $1.159 per liter. What is the cost of a 435 kilometer trip? Okay, so here what we have is, if we were going to set up an equation for this problem, we would start with the length of the trip, 435 kilometers, and then we use the relationship 6.5 liters for every 100 kilometers to set up this factor, 6.5 liters over 100 kilometers, matching the unit. And then we match the unit for liters, and we put down $1.159 per liter. If we work out the divisions, we end up with $1.159 per liter multiplied by 0.065 liters per kilometer multiplied by 435 kilometers. So these simplified forms come from doing the divisions. 6.5 divided by 100 is 0.065, and the unit is liters per kilometer. And this one, $1.159 for 1 liter. If we divide, we get $1.159 per liter. All right. Okay, so if we take a look at what happens when we do the multiplication here and end up with a number, again, what happens is similar to what happened with the money problem and the conversion of unit problem. Here we go from distance that we want to cover. When we multiply by 0.065 liters per kilometer, the kilometers cancel out and we get liters. So that's the volume of fuel that we need to cover 435 kilometers. And once we find the volume in liters, then we multiply by price per liter to find the total cost. And we go from volume to total cost. And now if we do the multiplication here, liters cancel out, we end up with dollars per kilometer. And it comes to roughly about 8 cents or 0.08 of a dollar per kilometer. And again, what happens is by multiplying these two values, we bypass the middle node, and we go from distance that we want to cover to the cost in one step. Okay, one more problem. And this problem is on chemical reactions. And this one says, what mass of CO2 is generated by the following reaction if the reaction generates 243 grams of H2O? The molar masses of CO2 and H2O are 44.01 grams per mole and 18.016 grams per mole respectively. And here's the reaction for it. So we've got the equation here. We start with 243 grams of CO2. Now, if you would like to do that, you can pause the video and take a look at how the equation was set up. But basically, I followed the same steps that we talked about in working with chemical reactions in an earlier video. And here now we have 3 of these factors. And that means that we go from, there is not just one node in between, but there are 2 nodes in between. And what we do is we go from grams of CO2 to moles of CO2. And then using the values in the chemical reaction, we go from moles of CO2 to moles of H2O, and then we go from moles of H2O to grams of H2O. If we multiply all of these values, we find a direct relationship between grams of H2O and grams of CO2. Now I let you go through the reasoning and draw diagrams like this to see how things work. And if you have any questions, put one down in the comment section and I will explain more. Okay, so if we work out all of these multiplications that are highlighted, we'll end up with 0.546 grams of H2O per gram of CO2. So about half a gram of H2O for every gram of CO2 that we use. For this particular reaction, of course, if you change the reaction, the relationship can change. But you see now we have bypassed all of this argument about moles of CO2 and moles of H2O, and we have found a direct relationship between grams of H2O and grams of CO2. Okay, algebra helps us to figure out multiple approaches to problem solving. And in fact, it is one of the major wonders of algebra that algebraic equations encode multiple approaches to the art of problem solving. No matter what approach you think of, it's embedded into algebraic equations. As an example of what I'm talking about, let's take a look at this problem. A book is priced at $43.75. It is on sale at 20% off. Tax is added at 13% of the sale price. Calculate the grand total. Now, With this problem, the way we would normally go about solving it, as we have done before, is to work out the sale price, and then we add the tax on top to find the grand total. So basically the steps are that we ignore the tax initially and work out the sale price. We only work with the discount, and then once we've worked out the sale price, then we worry about the tax and work out the amount of tax and add it to the sale price. And a very interesting question came my way once from a student who asked me if it's possible to do it the other way. Ignore the discount, work out the grand total. Imagine there is no discount. Add the tax to the original price, find the grand total, and then apply the discount to that grand total. My immediate reaction to that was, no, of course you cannot do that. But before I even finished my sentence, I sort of froze in my spot, because I realized not only can you do that, I'm willing to bet any money that you can do that, and it works. In fact, I would bet millions of dollars, and I would like somebody who's listening to this video to take me up on it. Even if you know you're gonna lose, that's okay. Because the reason I know that, and the reason I have so much confidence in it, because what I realized is that if you think about the equation that models the way we usually do things, like find the sale price and then add the tax to it, I'm going to display the equation right here. We get this equation. The grand total is, you start with the price, multiply by 80% to find the sale price, and then multiply by 113% to find the grand total. But if you think about it, multiplication there is this commutative property that says the order of multiplication doesn't matter. We can multiply 3 by 4 or 4 by 3 and we get the same value coming out. And therefore, multiplying 113% by 80% is the same as multiplying 80% by 113%. And we just change the order, and it still works. It's still the same. It will give us the same value, again, because the order of multiplication doesn't matter. So whether we start with the price, work out the sale price, and then the grand total, or start with the price, find the grand total, then apply the discount, it comes to the same thing. It's amazing. I actually had never even thought of that until this question came my way. And you see, one of the now, of course, we don't normally reason in this way. Normally, we go along the path that says work out the sale price, then work out the grand total, not the other way. But the thing is that I now know that it works, that either one works, and not just that. And here's the most important part. I have so much confidence in what I say. I have no doubt that you can change the order, and it still works. And this is what algebra does for me. In a step-by-step approach, the doubt would always be there. But here, we can see it, and we have no doubts about it. And that's what I find most attractive about algebra, that it gives you so much confidence in what you say. Okay, the next problem says a pen priced at $35.25 is on sale at 10% off. Calculate the sale price. And so for this, we would write it down as sale price is 90% of the price. If it's on sale at 10% off, then we pay 90% of the price. So sale price is 90% of the price. Now, of course, this question also always comes my way. What's wrong with saying that the sale price is price minus the amount of discount? So that's the question. What about work out the amount of discount and then subtract the amount of discount from the price? I have to admit that although when we formulate our equations following the algebraic approach, most often the kinds of equations that we prefer sort of map onto the way we normally reason in everyday life problems, when we deal with everyday life problems. For this particular problem, it's a bit different. I do very much realize that the common way to work out a problem like this is to work out the amount of discount, which is 10% of the price, and then subtract that from the price. However, we find that this other approach, where we find an equivalent percentage, the 90%, and then work out the sale price by multiplying it by the price, works much better when things get complicated. Now, before I tell you about this, more about this, let's take a look at these two equations. And you notice that they follow different approaches. So this is different approaches to problem solving that I'm talking about. Let's say 1% reasons like this by saying sale price is 90% of the price. Another percent reasons like this by saying sale price is price minus the amount of discount. Now, of course, algebra allows for both of them. There is a property called the distributive property of multiplication over addition. And it says if you're multiplying a sum like 3 plus 4 by a number like 2, you can either work out the sum, find the total, and then multiply by 2, or you can take the components 3 and 4 and double each one up and then add. This should make sense if you think about it. Think of brackets as a box, and inside it we have 3, let's say, pens that are sort of wrapped together, and then we have 4 pens as well that are wrapped together, so a group of 3 and a group of 4. The way to double the total is either take 2 boxes, which is what the top line says. In one box, represented by brackets, we have 3 pens and 4 pens. And to double the amount, we can take 2 boxes. And this one says to get twice the amount, double up each of these groupings of pens. Double up the 3 to 6 and double up the 4 to 8. And that also means that you've doubled the total. This is known as the distributive property. And the quick way we do it is by multiplying the number outside the bracket by every term inside brackets. So 2 multiplies both 3 and 4. And that's what's happening here. We are multiplying 35.25 by 1. That gives us the 35.25. And we are multiplying it by 0.1. And that gives us 0.1 times 35.25. The 1, of course, represents 100% of the price, which is why it turns into 35.25. That's the price. The 0.1 represents the rate of discount, of course, and if you multiply that by the price, you find the amount of discount. So the equation that we have, along with the distributive property, shows us that the two solutions will always work. They are always the same, so there is again no doubt that there will be no circumstances under which one may work and the other may not work. These are the same equations. 2 different ways to reason your way through the problem. Now, the reason that we prefer the top approach, 90% of the price, instead of price minus the amount of discount, is that as problems get more complicated, the second approach becomes, even now, I could argue that the second approach becomes a little bit less easy to manipulate. Let's take a look at a situation where we have multiple discounts, like in trade discounts. Problem number 8 says that a pen is on sale at 10% off. As a valued customer, you get an additional 5% off of the first sale price, and then tax is added at 13%. We want to find the grand total. And I guess I need to add that the pen, we didn't give you a price here, did we? No. The pen is priced at, let's say, what do we have? 35.25. Okay, so there we have. A pen is on sale at 10% off. As a valued customer, you get an additional 5% off of the first sale price. So first you have to find the first sale price and then find 5% of that as the second amount of discount. Then you add tax to the second sale price. Now for the grand total, if you think about how we would set up this equation, we start with the price. Then we find 90% of the price. That gives us the first sale price. So 90% of the price. And then we find 95% of the sale price, of the first sale price, to find the second sale price. So here we have it. This is now the second sale price. And then we multiply by 113% to find the grand total. Okay, so this is the way we would set it up, following recommendations that we had in earlier videos. Let's say we want to follow this approach, where sale price is computed by subtracting the amount of discount from the price. Then we start with the price, Now I'm leaving a bit of empty space on top because this equation is going to become long and I will need 2 lines for it. We start with the price, and then what we do is we find 10% of it. This is the first discount that we get, the first amount of discount. And now to find the first sale price, we have to subtract the amount of discount from the price. So we subtract this from the price. Now we have the first sale price. To find the second sale price, we have to find 5% of this one and then subtract it from itself. So we place this in brackets, find 5% of it, and then subtract it from the first sale price. And now to add the tax and find the grand total, we need to find 13% of what you see here, which is the second sale price. So let's place that in brackets and multiply by 0.13. Now this is the amount of tax. And we have to add the amount of tax to the second sale price, which is what you see inside square brackets. So we end up with this equation now. It's twice longer. And you might say that's not that big a deal, but there are other problems with it. What if the price is unknown, which is something we will look at in a few videos ahead. If price becomes unknown and the grand total is known, then this becomes this gets replaced by a quantity symbol, and so we end up with this equation, 34.06. Now we know the grand total is $34.06. That's 113% of 95% of 90% of the unknown price. If I do the same with the second equation, then this is what I get. There are many instances of price in the second equation, the 35.25. Whereas in the first equation, it appears only once. That's also true about the other numbers, 0.1. Let's take a look. Once, appears twice, 3 times, 4 times. 0.05 appears once, twice. And one of the problems with an unknown appearing multiple times is that the equations that you get will be more complicated. And in fact, decoding them is also easier with the top one. But to solve this equation, what we would have to do is to factor out a p from the expression that you see here, and then solve the problem. And when we talk about formulas, it gets even worse. When I take a look at this equation, I can tell you, by just looking at it, at a glance in fact, I can tell you that the total and the price are directly proportional. That means that if you double the value of one, the other one doubles up. So if something is twice more expensive, the grand total will be twice the amount. If something is half as expensive, grand total will be half the amount. And I have no doubt about this again, because this is what the algebraic equation is telling me, and I will teach you that. I will teach you by the time you're done with my videos. You'll be able to look at the same equation, and just like myself, you can tell that the grand total and the price are directly proportional. I don't see that in the other equation as easily, because for the grand total to be directly proportional to the price, there has to be either one term on the right side, which is what we have here, and p must be a factor within that term, and that's what we have. For t, grand total, to be directly proportional to price in this second formulation, p has to appear in every term and only once. And I'm not sure about that when I look at it, especially when it's not color-coded. I would really have to simplify this, and I would have to rewrite it in this form before I can tell that t and p are directly proportional. And this looks very, very cryptic right now. I can always make sense of that. This is like 90% of the price, 95% of the price. I'm trying to find sale prices, but I cannot really decode this at a glance. I can say, or even this one, I can say, okay, so this one is the amount of discount, subtract from the price to get the sale price, and then multiply by the second rate of discount, subtract from the... Now it's getting confusing now, you see? And so that's why we prefer the top formulation. Okay, and the last topic for this video is that you can always take algebraic solutions and convert them to step-by-step solutions. In the case of problems that we have been working on so far, where the unknown appears on the left side, this may not seem that it may not be that impressive. But as problems become more complicated, especially when the unknown starts to appear elsewhere in the equation, you'll find that this is a very powerful self-teaching tool. You may, so long as you can write an equation for a problem and solve it, you can always extract the steps for a step-by-step solution from your solution. Problem number 9 says a pair of glasses priced at $63.99 is on sale at 15% off. Calculate the sale price. So if I use the following logic to solve the problem, where we start with the price and we find 85% of the price, then I write my equation like this. If I want to now extract the steps in a step-by-step solution, for one thing, I notice that there will be 2 steps in a step-by-step solution. How do I know that? Because every time you do something, every time you add or subtract or multiply or divide, that becomes a step, or maybe a sub-step. I have one subtraction and one multiplication. There will be 2 steps in the solution to this problem following the approach that we have here. And if you think about how we would go about solving it, we would first work out the factor here. That corresponds to step number 1. And what we are trying to find is the percentage that goes with the sale price, 85%. Once we have it, then we multiply that by the price. That becomes step number 2, and that gives us the sale price. So the corresponding step-by-step solution is number 1, step 1, calculate the applicable rate for the sale price. And that's 1 minus 0.15, which is 0.85. So the sale price is 85% of the price. Step number 2, calculate the sale price. And for this, we multiply 85% by the price, and we get 54.39. So this is the step-by-step solution that I just extracted from the algebraic equation. Now let's say I use a different logic to solve the same problem. Instead of saying find 85% of the price, we go with the logic that says find the amount of discount and then subtract it from the price. The equation for that would be PS sale price is equal to price minus the amount of discount, which is 15% of the price. And if I wanted to turn this logic into a step-by-step solution, again, I would notice that there will be 2 steps. Now this time we would have to work out the terms. Term number 1 is done. Term number 2, we have to finish the multiplication, and then we can do the subtraction. This becomes step number 1. Once we've worked out the amount of discount, which is this step, then we subtract it from the price, and that becomes step number 2. And we find the sale price. So the corresponding step-by-step solution is step 1, calculate the amount of discount, which is 15% of the price. And so the amount of discount is $9.60. And then step number 2, calculate the sale price. And this is when we subtract the amount of discount from the price. And we end up with a sale price of $54.39. Okay everyone, so in this video I talked about some of the features of algebra which are quite often hidden to people who have sort of like basic skills in math. And I hope that you're starting to see how algebra can be used as a language and how algebra can encode so much information into it. And you haven't seen nothing yet. There is so much coming up. So please stay with me. Thank you very much for watching this video. And in the next few videos, I will be switching back to the technical skills component of the program. The next few videos will be dealing with the manner in which we work with rational numbers. Thanks again for watching, and I'll see you in the next video.